Welcome. This is Professor George Easton, and this is part 3 of the series of videos on measurement system evaluation. In part 3, I'm going to focus on evaluating the performance of a gauge using statistical process control. Now, as you know, metrics can be broadly divided into two types. The first type are continuous metrics or variables measures. And these are things like weight, height, and so on that are measured on a continuous scale. The other type of metric is an attributes measure. And in general, attribute measures classify things into groups. So they classify, for example, a part into defective or not defective. They might classify things by color, red, green, blue, etc., or gender, and so on. But attribute measures tend to classify the data into categories. Measurement system analysis methods are available for both continuous metrics and for attribute metrics. But the focus in this video is going to be on a gauge that is providing a continuous measure. So we're thinking about something like a scale for weight or a ruler or some other kind of measuring instrument that's going to measure length dimension. Measurement system analysis approaches for attribute measures are different. So the particular technique that I'm showing you in this video is not suitable for attribute measures. And dealing with measurement system evaluation for attribute measures will be left for a future video. Now, the method we're going to look at here is based on statistical process control, and it's really kind of an interesting, almost a funny method because it turns SPC on its head. In particular, in this context, when there are lots of points outside of the control limits, it's a good thing, not a bad thing. In regular SPC, of course, you want your process to be in control, and so you want essentially all of the points to be inside the control limits. But in this particular case, if there are lots of points that are out of control, that are outside of the control limits, it means that the gauge is capable. And just to remind you, a gauge is capable if the standard deviation of the measurement error from that gauge is less than 1/10 of the standard deviation of the thing that's being measured. Now, to understand the approach that I'm about to describe, you need to understand some things about control charting. In particular, you need to have a basic understanding of X-bar and R charts. You also need to understand how to estimate the standard deviation of a process using R-bar, the average of the subgroup ranges, and D2, the SPC constant D2. You also need to have some understanding of the idea of rational subgrouping. I'm not dealing with these topics here. As I say, this is essentially prerequisite material for understanding what I'm about to present. So basically, I need you to know something about SPC. Now, I'm going to first give you an overview of how this technique works, and then we're going to come back and do the details. But the idea here is to make repeated measures on each part. So I'm going to take a part, and let's suppose I'm measuring a dimension. I'm going to measure that dimension several times, repeated measures, using one measuring instrument. I'm then going to use these measures that were on that single part as a subgroup. So for each different part, I'll have a separate subgroup of measurements made with the same measuring instrument. What this means is that the range of those measures within a subgroup reflects only the measurement variation, not the part-to-part variation. So again, a subgroup is going to be formed by multiple measures on the same part. And so the only difference in those measures really should be the measurement error or the measurement variation. We're then going to set our 3 sigma control limits based on the ranges from these subgroups. So the 3 sigma control limits will be set only using the variation due to measurement error. And what I'm going to get is a picture that looks, hopefully is a picture that looks like the one that I've shown you, where the control limits are very tight and the vast majority of the data are outside of the control limits. This is a good thing. Out of control points are a good thing in this particular case, showing that the gauge is capable. So I'm now going to return to the details a little bit. So this is how you're going to make this chart. Again, I've taken each of my parts and I've measured each part repeatedly, and this forms a subgroup. And then for each of those subgroups, I'm going to calculate the range, and then I'm going to average the ranges for each of these subgroups to get R bar. Once I have R bar, I can estimate the standard deviation of the gauge, of the measurement error, by taking the R bar, the average of the subgroup ranges, and dividing by D2, where D2 is the constant from the table of SPC constants. And I'll show you this in just a minute. And what I'm going to want to do is set my control limits. What I'm trying to do theoretically is set my control limits at mu plus or minus 3 times the standard deviation of the measurement error, sigma sub MEAS, sub measure. And so I'm going to estimate these by setting my actual control limits at x bar bar. So x bar bar is now the average of the subgroup averages of the measures, plus or minus 3 times a standard deviation estimate for the measurement error, which is going to be given by R bar over D2. Now, if the standard deviation of the measurement process is small in comparison to the part-to-part variation, which it's supposed to be 10% or less, but if it's small in comparison to the part-to-part variation, most of the subgroup means, and the subgroup means are the average of the measures of the part, they'll be outside of the control limits. And the reason is that the part sizes are varying a lot, and the measurement error should be varying at about 10% of that. So if the measurement standard deviation is 1/10 of the process standard deviation, then more than 75% of the subgroup means ought to be outside of the control limits. And so the usual rule of thumb that's used in this case is that you want 80% of subgroup means to be outside of the control limits. Okay, so to be very specific about what we're doing, I have an example here, and in this particular example, the weight of a package is being measured in grams. So I have my first package here, package number 1, and what I've done is now taken the same scale and I have measured the package 3 times. So these are 3 separate measurements of the weight of package number 1, and that forms a subgroup of size 3. And then I'm going to do the same thing for the next package. So package number 2 gets measured 3 times. And so over here on the right-hand side, I've indicated the subgroup number and the average of the weights, and then the range of those weights. So the R is the range over here in the column furthest to the right. So I've done that for each of my packages. I've measured them, weighed them 3 separate times, computed the average of those weights and the range. X bar bar then is going to be the average of all of these X bars from the subgroup. So that's going to give me the center line of the control chart. R bar is going to be the average of all of these subgroup ranges. So R bar is going to be related to the standard deviation of the measurement process. Now, to convert the R bar into an estimate of the standard deviation of the measuring instrument, I'm going to use the constant D2 from the table of SPC constants. These constants are available in any book on process control, and I have reproduced them here. I'm going to go in this case to a subgroup size of 3, and I'm going to read off the D2 value that is 1.693. So I'm going to divide the R bar by 1.693 in order to get the standard deviation estimate sigma. And then I'm going to take that number and multiply it by 3 to get the plus or minus 3 sigma. That's the distance to the control limits in the control chart. So here's what my control chart looks like in this particular case. The center line is at x bar bar. The upper control limit is going to be at x bar bar, the center line. And the idea here is plus 3 standard deviations, where the standard deviation is the measurement error. So that's going to be plus 3 times r bar over d2. And then the lower control limit is x bar bar minus 3 times r bar over d2. And these control limits are very narrow because they only reflect the variation in the measuring instruments. I then plot my subgroup means, which is showing you the variation in the actual weight of the packages, which is supposed to be 10 times larger. And when I get this control chart, I get many, many, many points that are out of control. Now, if it's true that the standard deviation of my measuring instrument is 1/10 the standard deviation of the process, then more than 75% of these points should be outside of the control limits. And as I said before, the rule of thumb that people use is that you want 80% of your points to be outside of the control limits. So in this particular case, if I count things, there are 30 points corresponding to 30 packages. 26 are outside of the control limits. So that means 26 out of 30 are outside of the control limits, which is about 86%. So the gauge is capable because the percentage of points outside of the control limits is more than the 80% rule of thumb. Now, when you use this SPC method, you might as well go ahead and make the R chart and check that the measurement process is in control. So here is the R chart based on the ranges. And the ranges, again, only reflect the measurement error. And as you can see, all of these points are inside the upper control limit, so the measuring process appears to be in control. So note now that if you happen to be thumbing through the report from a DMAIC project, an improvement team, and you suddenly see a control chart where almost everything is out of control, you can conclude that they're probably doing a measurement system analysis. You might want to read the report in detail to check it, but that's the usual case when you see a control chart where just almost everything is out of control. So I want to address the issue of rational subgrouping in this context. And if you think a little bit about rational subgrouping, you're going to realize that you need to think hard about exactly what you want in the subgroups in this particular procedure, exactly what type of variation you want in there. In particular, if I use the procedure pretty much as I've described it so far, which would mean that I take a part and I measure it with a single measuring instrument by one person, then what's going to be in that subgroup is the repeatability. The repeatability is the variation of the gauge when it's operated by one person. And so what I'll be determining then is whether my gauge is capable by comparing the variation in the characteristic of interest to only the repeatability. But if I instead have in my subgroups not only repeated measures of the part made by one person with one gauge, but also repeated measures made by other people, then the variation in my subgroup will include the repeatability, the variation of the gauge, and the reproducibility, the variation among people. And so what I'll be doing is deciding whether or not my gauge is capable by comparing the variation in the process characteristic of interest to both the repeatability and the reproducibility. Now this probably reflects more realistically what's going to be happening in real life. I'm not going to just have the variation of the gauge. I'm going to have the variation of the gauge together with the fact that that gauge is operated by different people at different times. If I expand this to have not only repeated measures made on one part by one person using one gauge, but I include, as before, different people, so multiple assessors, but then I also do it at different times. And here I'm thinking about time not in terms of minutes or seconds, but different days of the week or different months, so it's longer time. So if I have all three of these things in my subgroup, then my subgroup contains variation due to repeatability and reproducibility and stability. Stability here is the term that captures the variation over time. Again, reproducibility is the variation between people, and repeatability is the variation of the instrument. And so if you think hard about it, you probably really want to use one of these last two cases, okay, where you not only include variation due to the gauge, but also variation due to the assessor and perhaps variation over time as well. So I want to briefly explain where the criterion of at least 80% of the points outside of the control limits comes from. Well, it comes from this probability calculation. So what's going on here? Well, if the measurement standard deviation is 1/10 of the process SD, then the control limits should be at plus or minus 0.3 sigma. And it's 0.3 sigma because the usual control limits are at plus or minus 3. So if we now think about all of this in terms of a standard normal random variable, a standard normal random variable z has a mean of 0 and a standard deviation of 1. So the regular control limits based on a standard normal would be at plus or minus 3. If our measuring instrument is precise enough that it has a standard deviation of 1/10 of that, that means that the control limits based only on the measuring instrument's variability are going to be at plus or minus 0.3. So if I take this standard normal random variable and compute the probability of being outside of these control limits, which I do by computing the probability that I'm inside the control limits and then subtracting that by 1, what I get is that this probability is essentially 76%. So what this means is that if the fraction outside is greater than 76%, then this is going to suggest that the standard deviation of the measurement instrument is less than 1/10 of the standard deviation of the process characteristic that I care about. So 76% or more means measurement standard deviation is small enough. And this 76.4% is rounded to 80%, and that's where the criterion comes from. So I'm going to close with the following summary. This SPC-based approach for gauge qualification to determine if a gauge is capable, it's very useful. It's pretty simple to do, and in fact it's kind of fun too, because it's turning SPC on its head. It's visual, and visual techniques are oftentimes a lot more powerful. But it is only for continuous variables. Okay, I need to emphasize this in the closing summary here. It is for continuous variables, and different approaches are required for attributes measures. But when you use this approach this way, you do need to think about exactly what variation you want in the subgroups, because you really do want to assess your gauge capability in comparison to the variation that you're going to experience in practice.